Dear students, welcome back to our discussion on air conditioning process. We have been studying about the various psychrometry process, and we discussed how we can represent these various psychrometry process on our psychrometric chart. Now let us discuss another term called bypass factor of a cooling or heating coil. Okay, so consider this case. Suppose we are keeping a cooling coil like this inside the direction of a flow of a moist air. Okay, so from point 1 towards point 2, a certain amount of moist air is flowing through, and we are keeping a cooling coil with a surface temperature, with a very low surface temperature as C. Okay, so the incoming air at temperature 1, it will be flowing through this channel, and when that incoming air is traveling in its path, some of the air molecules which is entering this path at 1, they may happen to touch the surface of the cooling coil. Okay, so those air molecules which actually happens to touch the surface of the cooling coil will be actually get cooled down by the very low surface temperature of the cooling coil, and those air molecules alone will be having a final very low temperature. Okay, and those air molecules which actually bypassed or which actually didn't touch the surface of the cooling coil will be remaining in its initial temperature itself. Okay, so when the air stream is moving forward and coming at the exit of this passage at 2, it will be a mixture of both cooled and uncooled air molecules. Okay, some air molecules will have been would have been cooled down by the cooling coil surface due to its very low temperature, but some of the air molecules may have bypassed, or they may have not touched the surface temperature or the surface of the cooling coil. So at the exit 2, the final stream of air coming out will be actually a mixture of both cooled and uncooled air molecules. Okay, so here we can consider this process, this cooling coil. The same case happens for a heating coil also. So whenever we are placing a heating coil, some air molecules may get heated up by that heating coil. Some air molecules may remain in the same temperature, which may have bypassed that heating coil. So this bypass factor we need to consider. This is a very important term in our air conditioning process. So in various air conditioning process, just like in the previous case, in the previous session, we discussed how we can represent the various psychrometry process. In that psychrometry process, we have discussed the sensible heating, sensible cooling, heating and humidification, cooling and dehumidification, like that. So this heating process is carried out by placing a heating coil, while the sensible cooling can be carried out by using a cooling coil. Okay, so we will be passing a very low temperature fluid, a working fluid, throughout this cooling coil, as a result of which a very low surface temperature C will be maintained in this cooling coil, and it will be producing the necessary cooling effect. Okay, so this entire concept of this cooling coil and this working is actually a mixing of the end product, or the end result will be a mixing of both cooled and uncooled air. So this is equivalent to mixing of two different air streams. Okay, so we can try to represent this cooling coil process in a meaningful psychrometric chart. So let the point 1 is representing the psychrometric condition, or the air conditioning condition of the incoming air. Okay, point 1 is representing the psychrometric condition of the incoming air, and point C is representing the surface temperature of the cooling coil. So why we are representing it on the saturated line? Because when we are considering in psychrometric terms, the surface temperature of the cooling coil is already at a very low temperature. In and around this surface in and around the surface of this cooling coil, whatever air molecules comes into contact with this surface of the cooling coil, its temperature will be drastically reduced and much below its dew point temperature, and those air molecules will be experiencing this dew formation, this excess water, the excess water vapor content in that air molecules, which happens to touch the surface of the cooling coil, it will be getting condensed, and whatever air molecules happens to come near this or come near and touch the surface of the cooling coil, they will be suddenly becoming saturated. So that is why the point C is represented on the saturated liquid line. Okay, so point C, actually it is called as apparatus dew point temperature. The apparatus dew point temperature means the surface temperature of the cooling coil, ADPT in short. So we will be learning about that in the later in the next session. So the incoming air from 1, it is actually moving towards the surface temperature, the surface of the cooling coil C, but only some air molecules will be actually touching and getting cooled by the cooling coil. Some air molecules will be remaining as such. So at the exit at point 2, a mixture condition, that is at point 2, the point 2 will be coming in between the line 1 and C. Okay, if all the air molecules which was at the incoming session happened to touch the cooling coil surface, what would have been the case? The point 2 will be situated at point C itself. That is, the entire air molecules would have been reduced to the surface temperature at C. But that is not happening in the practical case. Some air molecules will have actually bypassed the cooling coil C. So at the exit condition 2, the point 2 will be actually a mixture of both cooled and uncooled air. Okay, so this line 1C2 is representing this cooling coil action. Okay, so this bypass factor of a cooling coil or a heating coil is actually representing that amount of incoming air which actually bypassed this cooling coil. Okay, so from this term itself it is understood that is bypass factor is representing the fraction of that air molecules which was incoming at 1 but actually bypassed, or they which actually didn't touch the surface of the cooling coil, which actually bypassed and passed through a bypass route. Okay, so how we can represent this bypass factor? We can easily represent it using the dry bulb temperatures associated with this points 1, 2, C, or we can easily represent using the enthalpies associated with these points 1, 2 and C. Suppose we can find the dry bulb temperatures corresponding to 1, T1, then corresponding to 2, T2, and corresponding to C, TC. Okay, how we can represent? If all the air molecules actually touched the cooling coil, there would have been no bypass factor. That is the case, right? So point 2 would have been at C, but that is not the case. Some air molecules actually bypassed the cooling coil, and that is represented by the line. The air molecules which actually bypassed the cooling coil is responsible for this region C22. Okay, and the rest of the line 1 to 2 is representing those air molecules which actually touched the cooling coil. Okay, so if we can represent in terms of temperatures, T2 minus TC. Okay, T2 minus TC, that is T2 minus TC will be the temperature difference from 2 to C. That will be representing the amount of air molecules which actually bypassed the cooling coil. Okay, as a so how much is this air molecules, or how much is this portion of air molecules which bypass the cooling coil with respect to the total air molecules? That is the case of bypass factor. So T2 minus TC divided by the total change happening in the temperature. Okay, the total temperature change, that would have been the ideal case. Okay, T1 minus TC. T1 minus TC is the temperature change for which the cooling coil was set up. Okay, actually when we are setting up the cooling coil, we are actually aiming to bring down the temperature, the entire temperature of the air molecules, or the temperature of the entire air molecules from T1 to Tc. But that is not happening. Some air molecules are actually bypassing the cooling coil, and as a result, a new temperature T2 is coming up. So T2 minus Tc is representing those air molecules which actually bypass the cooling coil. Then T1 minus Tc is representing the ideal temperature drop for which the this cooling coil was set up in the path of this in the path of this moist air. Okay, so bypass factor is represented if it is represented in terms of temperatures, it will be like this: T2 minus Tc by T1 minus Tc. That is T2 minus Tc. What is this percentage compared to the total temperature change? T1 minus Tc. T1 is here, T2 is here, Tc is here. The same case we can apply for in the case of enthalpy also. The same way we can represent the bypass factor H2. So enthalpy corresponding to 2 is H2, enthalpy corresponding to 1 it is H1, and corresponding to C it will be Hc. So H2 minus Hc will be representing the bypass the air, and H1 minus Hc is the actual enthalpy drop for which the or the ideal temperature, ideal enthalpy drop for which the cooling coil was actually set up. Okay, but that didn't happen actually. So H2 minus Hc by H1 minus Hc is also another representation for this bypass factor. Okay, then if we want to represent the efficiency of the cooling coil, that will be simply 1 minus bypass factor. Okay, so 1 minus bypass factor means it will be focusing on mainly this area 1 to 2. This area this section 1 to 2 is actually representing those air molecules which actually came into contact with the surface of the cooling coil and actually got cooled. Okay, they didn't bypass the cooling coil, and the efficiency or the cooling capacity of the cooling coil is actually represented by the line 1 to 2. 1 to 2 is representing the cooling action produced by the cooling coil. Okay, then in the starting of today's discussion, there was a term coming up like this: apparatus dew point temperature, or ADPT in short. Okay, so that explanation is very simple. If the surface temperature of the cooling coil is same as the dew point temperature of the incoming air, more or less it will be set like that, then some amount of water vapor it will be start condensing from the air. Okay, and that will be the excess water vapor corresponding to that dew point temperature. Now the cooling coil temperature is called as the apparatus dew point temperature. More or less the surface temperature of the cooling coil C will be set at a very low temperature corresponding to the dew point temperature of the incoming air. That is mainly from the experience. Okay, experience of the industries working in this air conditioning field. Okay, so that is the case of this bypass factor and this apparatus dew point temperature. So all of you learned this thoroughly. This apparatus dew point temperature and this bypass factor, it is repeatedly asked in the university exams. So thank you.